Traditionally, the best and sometimes the only way of finding out whether or not a new design or product is practical and acceptable is to build it and try it out. The same principle holds true for decision-making in almost any aspect of human affairs. The test of the idea or decision is the test of reality. However, when we can build and test a model of a design or a real-life situation, we frequently can save a great deal of time, money, and grief. And the most powerful of the many kinds of models are mathematical and logic, which can be manipulated and tested on the most versatile of modern man's inventions, the electronic computer. In this high-speed technological world of ours, a misplaced decimal point or an incorrect number can mean an error of gigantic magnitude. But even more serious is the error of not having adequate current information available to us. And in the highly competitive business world of today, the penalty, even for small errors, is suddenly very high. To an increasing degree, we seek the ability to predict the consequences of our plans and actions before putting them into effect. It is probable that many businesses today have considerably less latitude for trial and error in planning and decision-making than they assume they have. So much of our decision-making depends upon our ability to handle and to interpret information. In science and in business, our store of information increases more rapidly with each day. How are we to handle the sheer volume of information so critical to informed decision-making? Within the past several decades, methods and machines have been devised which have become invaluable extensions of our information handling and decision-making ability. Accurately and tirelessly, electronic computers can trace out the consequences of 1,000 possible actions, can pick out the best design among thousands of possible designs, thus providing a better base for the informed exercise of human judgment. Whenever the elements and operations of a system can be quantified or expressed in measurable terms, a mathematical model of the system can be constructed and manipulated on a computer. This technique is known as simulation. For example, the performance of this, the most powerful of America's space vehicles, the design of this chemical plant, and the operation of this, the world's largest sugar refinery, were simulated in advance of actual construction or operation by means of models made entirely of equations and numerical data manipulated on a digital computer. Where once we had to build something in order to test it, we can now simulate and test the performance of machines, of chemical and other processes, and even complex human organizations by means of electronic computers. On this computer at the Marshall Space Flight Center in Huntsville, Alabama, mathematical formulations relative to the design and desired performance of the Saturn rocket were processed, improved, and reprocessed many times. In other words, a mathematical mock-up of the rocket was tested and studied before an actual test was offered.
We have just witnessed a static test of the booster stage of the Saturn space vehicle. The Saturn space vehicle is the largest one at the present time under design in the United States.
This is Dr. Helmuth
Will
Holzer,
develop,
head of the computation laboratory at the Marshall Space Flight Center.
and it will have 1.5 million pounds of thrust. The purpose of this test was to find out lots of things about the engines. We wanted to know whether the engines really developed that many horsepowers and whether we had that many pounds of thrust. And we want to know whether our fuel consumption was right and whether we had excessive vibrations and what were the frequencies of those vibrations. We also wanted to know lots of things about the interactions of the 8 engines we have to propel the booster. And things like stress and strain and heat protection and so on. But we wanted to know more. We wanted to find out whether our predictions arrived from a mathematical model or mathematical techniques for this test were right.
Computers have played an extremely important but relatively unpublicized role in America's space program. Only a computer, for example, can handle the vast quantity of computations necessary in calculating a trajectory. And in relation to the design work on the Saturn, Dr. Holzer commented,
If you can only save one single Saturn firing by using computers, you can pay for quite a number of high-speed digital computers. And this is why it is just absolutely necessary to use mathematical models and their solution by computers to proceed in this design. So the whole process works about like this. We start out with some idea, and we still don't know enough coefficients and enough actual values, so we take the best thing we have and come up with a mathematical model. Then we start designing something or some parts, and after we have the parts, we test them and make sure in the test that either we have made the right assumptions or we gain new experience. We then improve our equations and come up with new results, make new tests, improve our equations again, and so in this, using this cycle, we finally then come up with a complete design. And then after we have this, we want to make sure that once this vehicle goes to the launching pad, that the first firing will be a success.
The first launching of the Saturn was a success, due in no small measure to the many simulated firings run on the computer before the actual launching of the bird. A team of engineers and mathematicians used a computer to select the economically optimum design for this chemical plant. In fact, in a final test of the system, the computer designed a chemical plant that would cost between $250,000 to $600,000 less to build than the best previous design of a group of engineers. The system is called CHEOPS, for Chemical Engineering Optimization System, and is explained here by Dr. Thomas Barron, Director of Engineering Research for the Shell Development Corporation.
CHEOPS is a system of designing chemical plants. To start with, I probably should show you what a typical chemical plant looks like. Let's assume that we wish to convert in a reactor, which I'm just drawing, a reactant which I will call R. I want to make out of this reactant R a product P, and this reaction occurs in this vessel. Now, the difficulty is that not all of the reactant is converted into the product, only part of it. Now, the bigger the vessel, the more of the reactant is converted into the product. Now, somewhere along the line, I have to separate the product that I have obtained from the reactant. And this is done in, say, a distillation column or some other separation unit. The unconverted reactant is cycled back to the reactor. So this is still a reactant, and out of here comes the product. Now, this is an oversimplified plant, but a typical one.
The CHEOPS program works with 3 different sets of information. First is the logic program, containing the instructions for what the machine is to do. The second contains information on the units that make up a chemical plant, such as reactors and distillation columns. There is also information on how the various process streams flow and interconnect, along with the many limitations on operating temperatures and so on. The third set of data contains technical information on the process streams and economic and legal information, such as the cost of piping, labor rates, and even zoning restrictions.
A typical plant would involve such variables as pressure, flow rates, and a number of maybe as many as 50 to 100, 250 variables that we have to look at. But we're always interested in finding that set of all these variables which makes the whole thing the cheapest. Now, by cheapest, I mean not only that it's cheapest with respect to the materials that are consumed and the labor that goes into building the plant, but I'm talking about the amortized cost of the product, which includes the cost of the vessels as well as the operating costs the plant is running. So, generally speaking, then, the problem is to minimize this amortized cost of the product. And this will depend, and I will write this the way a mathematician writes it, I will say that it's a function of, but all I mean is that it depends on. This will depend on a number of things. And the number of things it depends on I will call x1, x2, x3, and as I say, I may have several hundred of these x's.
With its bundle of mathematical information supplied by the engineers, the computer, following the instructions in the CHEOPS program, works out its first design. Then, following instructions, the computer begins, in effect, to ask itself questions. What happens if the temperature in the reactor is raised 5 degrees? Or what if the amount of chemical A in the feed stream is increased from 49 to 51%? The computer designs a plant based on these changes. If the design is an improvement, it changes all of the appropriate variables in the direction of the improvement, and so on over and over again until further changes in the variables fail to produce a more economical plant. The computer then has reached the optimum design. It stops computing and prints out the results.
CHEOPS is a system which includes the mathematics required for optimization, for seeking the maximum or the minimum, with all the things that can be said once and for all about chemical plants. This includes instructions for the machine on how to accept data from engineers, on how to print out so that even executives can understand what is being said, on how not to violate obvious laws of nature. For instance, the number of pounds that enter this plant have to equal to the number of pounds that leave it. The amount of energy that enters the plant has to equal to the amount of energy that leave it, and so on. Now, all these things are done once and for all. This is approximately 80% of the work, total work, that has to be done as far as instructions to the machines are concerned. Now, the other 20% have nothing to do with mathematics. It simply represents feeding of data in which the engineer tells the machine what is different about this plant, what distinguishes this plant from all other plants, this particular reaction from all other reactions, and this particular flow scheme from all other flow schemes. Now, I would say that the creation of this system, this generalized system, which we call CHEOPS, took 15, 29 years. The application of CHEOPS, the instructions of to the machine, in a particular case, take anywhere from 2 man-months to, say, a man-year, depending on the complications of the plant. Now, the machine may take, in a single optimization and seeking the optimal ones, anywhere from a few minutes up to a few hours.
An accurate mathematical reflection of exactly what happens under a given set of operating conditions in the world's largest sugar refinery can be worked out on a computer in approximately 30 seconds. In this book, there are several hundred representations, each illustrating what happens in a refinery under a slightly different set of operating conditions. This information could not possibly be obtained if the refinery itself had to be specially set up for each such test. These simulation studies are possible because of the development of a mathematical model programmed for the IBM 1401 computer and designed to reflect the average 10-day output of the refinery under a variety of conditions and levels of operation. We asked Richard Brooks, coordinator of operations research for the C&H Sugar Refining Corporation, about this work.
During the past several years, the production requirements that were placed upon the Crockett refinery were such that it became virtually impossible to conduct various tests within the refinery itself. As a result, top management authorized the development of a mathematical computer model of the refinery. The hope was to develop a type of analytical pilot plant for the refinery itself. The study brought together the technical know-how of the refinery.
Neil Pennington, chief chemist, research for C&H.
With a competence in operations research.
Earl Isaac of the management consulting firm of Fair, Isaac & Company.
The final result was a simulation model of the refinery. It involved the interaction of 500 variables in 100 product flows and takes 80,000 steps to complete.
With this simulation model, we can now make test runs to determine whether or not a particular change in a process variable or an input variable will give us a improvement in our plant processing.
By describing the components individually in a mathematical sense, and then describing the way in which they interacted also in a mathematical form, it is possible to infer how the overall system will operate under conditions that have not been encountered in actual practice. So in that sense, it is a pilot plant where the knobs can be twisted. In this case, the equivalence is changing the numbers within the computer to arrive at unknown operating points.
This simulation model is able to measure in terms of color, purity, and quantity, end products and intermediate flows, the effects of variations in melt rate, raw sugar blends, raw sugar polarization, raw sugar color, and sales demand. It is, in effect, an analytical pilot plant where the effect of certain refinery decisions can be measured individually and in terms of their effect on the whole refining process. The computer prints out its answers on a flow diagram of the refining process. Each of the boxes represents a step in the refining process, beginning with the transfer of the raw sugar from the bins to the melt house. The sugar crystals are then dissolved in large melt tanks, and the liquid is then sent to the char house to undergo 2 types of filtration. From the char house, the liquid sugar is separated into various grades and sent to the vacuum pans for crystallization. The refined sugar is then dried in large granulators, sorted according to crystal size, and packaged in a variety of package sizes and grades. This simulation model of the refinery is not the first model to be used at C&H, as Richard Brooks indicates.
We started off 3 or 4 years ago and developed a simulation model for the shipment of raw sugar from the Hawaiian Islands to Crockett, where our refinery is located. This past year, we have just completed a simulation model of the refinery itself, and we have on the drawing boards ideas for models which will predict sales, determine the net financial return to the corporation, Our general thought is that perhaps in the fairly near future, we will integrate all of these models to have a truly systems-wide model of the entire operation of the company.
Designers, architects, engineers, and scientists have been using three-dimensional models for a long time. These, for example, are models of various kinds of viruses. But the kinds of models we are interested in here are mathematical models of operating or dynamic business and industrial systems. The books that a company accountant keeps are a simplified model of the flow of goods and services through a business organization. From the books, it is possible to measure such things as rates of flow, to measure the performance of various parts of the company, and to determine the values or profits produced. Businesses have always had models of this sort designed to give a current picture of a company's condition. But in addition to wanting to know where the company stands today, the manager also wants to be able to predict where the company may be in the future. Did managers make decisions based on mathematical models prior to the recent scientific developments in business management? We asked Dr. Ernest Königsberg, professor of industrial engineering at the University of California.
Well, the funny thing is they must have used them whether they recognize it or not. I have heard a manager say that, well, we really don't use any forecasting. We just say that next year's business will be like this year's, which is the equivalent of making a forecast. And generally, when they make decisions about changes, they are doing it in terms of a model which may be very poorly defined and ill-defined, but somewhere in their mind they have a picture of the effects of their action.
The modern business executive has been described as an information converter. That is, a man who converts information into decisions which trigger actions designed to obtain certain objectives. Frequently, his main problem is to decide which information source has priority over another. When there is irrelevant information, and when there are a great number of minor decisions required, it is altogether too easy to lose sight of the possible effects of a single decision throughout the total company operation. Ideally, the executive needs a method which enables him to study the parts of the business in relation to the whole operation of the company, and a means of tracing out in advance the effects of decisions throughout the system.
The point is that the president of the company is involved in day-to-day business, and he has to consider actions on a day-to-day basis. He doesn't have time to sit back and consider the relationships and interrelationships within the business. He generally doesn't have the mathematical background to develop a model that is accurate and workable. Even if he could write a model, he couldn't carry out the necessary calculations. I'm sure he can understand the result once he got them.
But first, the results must be produced. Under the generic title of Operations Research, methods first developed by scientists in relation to military strategic and tactical problems in World War II are today being applied to many business operations, particularly the petroleum industry.
I don't think there is a petroleum company that is not making extensive use of operations research, in particular linear programming and extensions of linear programming. They have to stay in business.
Linear programming is a mathematical technique used in operations research whereby a business system is analyzed into its basic components or activities, and these elements are then manipulated in such a way as to optimize profits or minimize costs for the system. And the high-speed computer is an essential tool for this kind of practical business research. Mathematical models for business problems that can be fed to a computer range from what combination of raw materials and manufacturing resources will result in the most economical production of a given product, to the problem of selecting sites for new plants and stores so as to maximize profits and meet customer demand. Frequently, the single mathematical model can be applied to many different kinds of businesses. As Professor George Danzig, widely heralded as the father of linear programming, commented,
"Well, a standard joke in my house is that when I come home in the evening, my children ask me, 'Daddy, what industry are you in today?' This gives some index of the broad number of applications."
Most management decision-making involves many alternatives, rather than a simple choice between one decision that is right and another that is wrong. Today, the sheer volume of information to be considered and the complex interdependence of the factors involved are more than the unaided human being can handle. Electronic computers, together with techniques such as linear programming, are creating a revolution in the field of business management and decision-making. Without the computer, there are many problems involving information and control which we simply could not solve. Increasingly, the computer is being used as a kind of electronic library, making available information which would otherwise be too costly and time-consuming to obtain. It is the computer that gives the manager the ability to predict the consequences of decisions and the future state of a business system. And it permits the manager to make better informed decisions, all of which adds up to increased power and knowledge, which is a property of men, not machines.
Within 10 years, it will be obvious to everybody that a revolution has already taken place.
You can couch a problem directly in computer terms and arrive very economically and readily at a solution. So you're thinking in broader principles and structures and interrelationships rather than in the small and very arduous component-limited thinking that you're restricted to before.
The problems that high-level management will face will continue to exist, and computers will make some contribution to them. But I don't think that we're going to replace the manager. And not all the middle-level managers are going to be replaced either. So that it's a revolution, but let's say it's not so bloody. It's got some friendly characteristics.
This is NET, National Educational Television.